Hello everyone and welcome to this memory map. Today we're discussing the kinetic theory of gases. Now the kinetic theory of gases helps us get insight into two very important things. One is the behavior of gases and the other is that it helps us link the very big to the very small. Behavior of gases is studied better with kinetic theory because it was found that even different types of gases exhibit similar uniform properties at the bulk level. Similarly, kinetic theory of gases is connecting the very big to the very small by helping us understand the properties at a macroscopic level by looking sometimes at the microscopic properties. That is, by maybe studying a molecule, we'll be able to tell about the nature and behavior of the entire gas as a whole. So let's begin the kinetic theory of gases. The first question that comes to mind is that why is the study of gases important at all? And we began to answer this question in the chapter on thermal properties. There we saw that in measuring temperature, the property of expansion of mercury was used. Mercury absorbs heat and expands in reaction to this, and this expansion is what we measure in the thermometer. However, we also saw that if thermometers are made of different liquids, then even if they were properly calibrated, then even the readings were not uniform for different liquids. And then a very important observation was made that the same problem was not prominent in case of gas thermometers. Gases showed a considerable uniformity in the readings, which means that even if I took gas thermometers which had two different gases, then if they were properly calibrated, we saw that their readings were largely accurate and uniform. And this is what I mean by the fact that overall at the bulk level, most gases show a uniform behavior or nature when it comes to similar properties. And in fact, in a gas thermometer, we were using the property that a change in pressure of a gas is caused with temperature. For example, here you have a gas thermometer and the substance whose temperature is to be measured is placed in contact with the bulb of the gas thermometer. The heat from this substance is then transferred to the bulb, and from the bulb it goes to the gas which is inside, and then because of this the temperature of the gas changes, that there is a change in the temperature of the gas, and we just said that this change in temperature causes a change in pressure, and it is this pressure difference that we use to measure the reading in a gas thermometer. So the first thing that we must revise are the gas laws. Let's take a look at them one by one. The first law is Boyle's law. Boyle's law simply says that pressure and volume are inversely proportional given that the temperature remains constant. So this means that if I decrease the volume of a gas, I will see an increase in pressure given that the temperature of the system does not change. And therefore Boyle's law is simply saying that PV is actually a constant. Now if you plot the graph of PV is a constant on a PV graph, you will see this dotted line as you can see in the picture. However, when we plotted the experimental values of these gases, we saw that this was not following the dotted line as it should. We got different graphs for different temperatures. But as the temperature went on increasing, that is T1 is at a higher temperature than T2, which is at a higher temperature than T3. And so we saw that when we increased the temperature of the gas, it got closer and closer to this dotted line, which means that Boyle's law is very well followed at high temperatures and low pressures. Now we also know that volume is inversely proportional to density, and therefore instead of saying that pressure and volume are inversely proportional, I can say that pressure and density are directly proportional, and therefore instead of writing PV is a constant, I can write P by density is a constant, and therefore I get P1 upon rho 1 is equal to P2 upon rho 2. The next gas law that we must revise is Charles' law. Charles' law is pretty straightforward. It says that volume and temperature are directly proportional, which means that if I heat a gas, it will cause an increase in its volume, and therefore I say that volume and temperature are directly proportional. And again, this means that V by T is a constant. And again you see that if I try to plot the graph for V by T is a constant, I will get this dotted line. And again I tried to plot the experimental values on this graph, and I saw that the graph was not following this dotted line. But you could see that at low pressures and higher temperatures again, the gas was coming close to the behavior of this dotted line. And therefore we say that the gas again was following Charles' law for low pressures and high temperatures. Now again I can also say that volume is inversely proportional to density, so instead of writing V by T is a constant, I can say that rho T is a constant, and this is how I get rho 1 T1 is equal to rho 2 T2. The next law that I must revise is the Gay-Lussac's law. Gay-Lussac's law is simply saying that pressure is directly proportional to temperature, and when I plot P by T is a constant on a graph, I should get straight lines because P and T are directly proportional. Now, there was one interesting observation to be made about these graphs. No matter which gas I plotted this graph for, I saw that the graph was not starting from the origin, which means that even when I am at 0 degrees Celsius, the pressure was not dropping down to 0. So the next obvious question to scientists was, how much should I drop this temperature that the pressure goes down to 0? And they exactly did this. They saw that when they extend this line in the graph backwards towards the negative axis of temperature, they saw that at the temperature minus 273.15 degrees Celsius, the pressure was dropping down to an exact 0. And this temperature is exactly what we call as the absolute temperature. And we saw that a graph of pressure versus temperature for various gases showed that at absolute 0, no pressure was exerted. Finally, we must also revise the Avogadro's law. Simply speaking, it says that equal volumes of all gases under similar conditions of temperatures and pressure contain an equal number of molecules, which means that if I try to blow up 3 balloons which are of the same size, which means they have the same volume, and if I try to blow them up using 3 different gases, as long as the pressure under which I am filling this balloon is the same and the temperature of the system remains the same for all 3 of them, it means that the number of moles that I will find inside each of these balloons will be exactly the same. And therefore, I can say that Avogadro's law says that volume is directly proportional to the number of moles given that the temperature and pressure is constant. So I can also write this as V1 by N1 is equal to V2 by N2. So now finally let's talk about the kinetic theory of gases. Now the kinetic theory of gases is based on the molecular picture of matter. In solids, the intermolecular separation is negligible and therefore the intermolecular forces can definitely not be neglected. However, in liquids we know that the intermolecular separation is quite large as compared to that in solids. But even then the intermolecular force, even though it is reduced, it's not reduced so much that it is still substantial and hence even in liquids the intermolecular forces cannot be neglected. However, when it comes to gases, the intermolecular separation is quite large. In fact, it is much larger than the size of the molecules themselves, and due to this the intermolecular forces are substantially reduced and can be neglected. In fact, this is the most fundamental assumption of the kinetic theory of gases, that is, the intermolecular forces between the gaseous molecules can be neglected. Of course, there are some other assumptions, that is, the size and volume of the molecules is very less as compared to the size and volume that the entire gas occupies. We also assume that the molecules are perfect elastic spheres. We also say that these molecules must be traveling in a straight line and they only change their directions when they collide with other molecules. And these collisions which happen between molecules and with the walls of the container in which the gas is placed, these collisions are also assumed to be completely elastic, which means that the kinetic energy is always conserved and the total momentum is also always conserved as usual. So this is the overview of the kinetic theory of gases. The starting point of the kinetic theory of gases lies with the ideal gas equation, and we arrive at this equation using the laws that we have already seen, that is Boyle's law and Charles' law. Boyle's law says that PV is a constant, Charles' law says that V by T is a constant. If I combine these two, then I will get that PV by T is a constant, which means that PV is equal to some constant into T. Now this some constant turns out to be N times Kb, where N is the number of molecules and Kb is the Boltzmann constant. And therefore this is the ideal gas equation or the equation of state. But this can also be written in another way. We can also say that PV is equal to small n R T. This is the ideal gas equation for n moles of an ideal gas. So obviously here then n means the number of moles and R is the universal gas constant. Now if this is the equation for n moles of an ideal gas, if I ask what is the equation for 1 mole, then obviously you will put n is equal to 1 and it will become PV is equal to RT. But 1 mole has Avogadro number of molecules, and therefore if I ask what is the equation for 1 molecule of an ideal gas, then I simply have to divide that R by Na and I will get that PV is equal to R by NaT. But R by Na is nothing again but the Boltzmann constant itself, so I say that PV is equal to KBT is the ideal gas equation for 1 molecule of the ideal gas. Now formula I can also write what is the ideal gas equation for m grams of an ideal gas, and it comes out to be PV is equal to mRT, where R is the specific gas constant. So this is the ideal gas equation. But I am saying that it is the ideal gas equation again and again, but I haven't defined what exactly is an ideal gas. So let's take a look what happens when I actually plot this on a graph. I tried to plot PV by T on a graph with respect to pressure, and I saw that I should be getting this straight line which I have marked as the ideal gas line. However, experimentally when we plotted the values, we saw that these graphs were not straight lines. But we noticed something that we have already discussed once. We noticed that as the temperature of the gas was increased, these lines became more and more closer to the ideal gas line. So obviously T1 has a higher temperature than T2, T2 is at a greater temperature than T3. So as the temperature of the gas was increased and the pressure was decreased, we saw that the gas was approaching ideal behavior. And from this I can say that gases approach ideal behavior at high temperatures and low pressures. And now I want to finally say what exactly is an ideal gas. An ideal gas is one which follows this equation at all temperatures and all pressures. We said that the kinetic theory of gases helps us understand the link between the very big and the very small. And the kinetic interpretation of pressure is one such major example. Now, pressure overall is a macroscopic quantity. That is, we look at the pressure of a gas overall. But we are going to study this by looking at what the molecules are doing, and therefore we are linking the behavior of the molecules to the behavior of the gas as a whole. So let's see how to find out the pressure exerted by the gas on the wall of a container. Firstly, we must remember that the molecules of a gas are in incessant random motion. This is an assumption of the kinetic theory of gases. We also say that they collide against one another and with the walls of the container. All collisions between the molecules among themselves or between the molecules and the walls of the container are elastic, which means that we said that the total kinetic energy will be conserved and the total momentum as usual is conserved. So let's just think about this for a moment. I'm saying that if I want to find out the pressure exerted by the gas molecules on a container, first I will take a look at the pressure exerted on one wall of the container. So now let's start with this understanding. We're saying that a box has N is equal to the number of molecules, and the volume of this box is what I will call as capital V. So now I want to find what is the change in momentum of one molecule when it is colliding with the ball. I want to find what is the change in momentum of one molecule when it collides with the wall. This is the collision which will cause a pressure on the wall, and we will count this change in momentum for all the molecules, which together will give the total pressure on one wall of the container. So here I have this molecule which is moving in the x direction. I'm going to count only the change in momentum in the x direction because my wall is only affected by the molecules which are moving in the x direction. And therefore now what I will do is I will start counting the number of collisions that the molecules are making with this wall. So I say that I'm going to observe the molecules and I'll see that okay, one molecule hits the wall and therefore this is the first collision, and similarly I will continue to observe that at some other point there will be another molecule hitting the wall which will be the second collision, and so on and so forth. So in total I will count the number of collisions that the molecule has with the wall, and for each collision I will write down the change in momentum. And why am I doing that? Because once I have the change in momentum for all the collisions, then I will get the rate of change of momentum. From the rate of change of momentum I will get the force, and force per unit area will give me the pressure exerted by the gas on one wall of the container, and therefore I can say that the force on a wall is the rate of momentum transfer due to the collisions. Every time a molecule collides with the wall, it transfers momentum, and this rate of momentum transfer gives me the force exerted by these molecules on the wall, and overall the pressure exerted by the gas will be found by finding this force per unit area. And if I do that, I will get the pressure exerted by the gas on the wall of the container. Remember, in our case right now when we discussed the example, we were talking about the molecule with a speed which was moving in the x direction. Overall, you'll have to find this for all the directions, and it will give you that the pressure exerted by the gas on the wall of the container is 1 by 3 rho c square, where rho is the density of the gas, c is the root mean square speed. And we will study what the root mean square speed is in a little detail in a little while, but for now remember that the pressure comes out to be 1 by 3 rho c square, which is also written as 1 by 3 nm upon vc square, which can also be written as 1 by 3 capital MC square by capital V. Now here n by V, that is Number of molecules per unit volume is denoted by small n with a subscript v. It can also be written as 3p by mc square. This is the number of molecules per unit volume. So this is how we obtain the pressure from the kinetic theory of gases. We'll also revise one more thing with respect to pressure. That is the Dalton's law of partial pressures. Now Dalton's law of partial pressures is pretty easy to understand. It's basically saying that if you have a mixture of non-reactive ideal gases, then the total pressure exerted by all the gases is nothing but the sum of the individual pressure exerted by each gas. So if I say that the total pressure exerted by this mixture is capital P and the pressure exerted by each of the gases is P1, P2, P3, then the total pressure is the sum of P1, P2, P3, etc. So if I use the formula for pressure that we have just derived, I will get that P is equal to P1 plus P2 plus P3 and so on and so forth, which will be nothing but 1 upon 3V in bracket N1 plus N2 plus N3, where each of these is the number of molecules per unit volume multiplied by mc square. Let me show you what this means pictorially. In this case, V is the total volume of the container, N is the number of molecules per unit volume of each gas, and C is the RMS speed. Now let me show you what I mean by this pictorially. Suppose I have this box which is full of gases which are not reacting with each other. Here you can see I have 3 gases because there are 3 different colored molecules, red, green and blue. And therefore I'm asking the question, what is the total pressure exerted by the gas? And I say that okay, the total pressure exerted by the gas is P. But instead of looking at the total pressure of the gas, if I first look at the pressure that only the blue molecules would have exerted if they were only alone there in this container, and I say that this pressure would have been P1, and then I say that okay, what if only the green molecules would have been there in this huge volume, capital V, then what would have been the pressure they exert? Then that would have been P2, and then I say that okay, if red molecules alone were there in this big volume, the pressure that they would have exerted would be P3, then I say that the total pressure that they are exerting right now is equal to P is equal to P1 plus P2 plus P3, and therefore to find the total pressure exerted by a non-reactive mixture, all you have to do is assume that each of the gases are sitting alone in that whole container, ask what each of their pressures are, add them up, and that will give you the total pressure. Now the next thing that I want to do is talk about the speed of gaseous molecules. According to the kinetic theory of gases, we already know that all the gaseous molecules will always be moving in a random motion in random velocities at any given temperature, which means that some of these molecules might be moving really slowly while some others might be moving really fast. In fact, because the motion of all these molecules is random, it is also possible that their sum of velocities will equal to 0, because velocity is a vector quantity and you could have molecules which are moving in the exact opposite direction. The question about all of this is that how do I comment on the overall speed of the gaseous molecules? All of these molecules are moving with different velocities. So let me give you a very simple example. If I want to comment if a particular class is good at math, what I will do is, instead of looking at each and every person's maths marks, what I will do is ask what is the average of the maths score in the class. So therefore average is a way of looking at an overall picture where lots of different individual items are involved, and therefore the first thing that we calculate for the speed of a gas molecule is the mean speed, which is sort of an average. By definition, it is nothing but the sum of the speeds of all the gas molecules divided by the number of the gas molecules, and this is exactly how we find the average in other cases. But finding the average is not always enough, because like I said, you could have velocities that were in opposite direction, and because velocity is a vector quantity, you'll have a plus velocity and a minus velocity, and then this will become 0, and therefore the average will not give you any sufficient information about these velocities. So to avoid this error where we have opposite velocities going out to be 0, we have a different type of calculation of velocity, that is the mean square speed velocity. In this, what you do is you square all of the speeds first, and therefore what you are adding will always be positive quantities, and therefore no information will be lost. And therefore mean square speed does what? It just adds up all the squares and divides it by the total number of molecules. Another third type of very important type of speed that we calculate for a large number of molecules is the root mean square speed, which is nothing but the root of the square of the mean square speed that you just calculated. That is, again, you add up the squares of all the speeds divided by the total number of molecules, and then in the end take the root. So as the name suggests, Root mean square speed means first you take the squares and then you take their mean and then you take the root, and this gives you the root mean square speed. Now, using this logic, we can actually plot the velocities of different gas molecules on a graph, and this is nothing but the Maxwell distribution. The Maxwell distribution is basically the plotting of all these different values on a graph, and the question is that even though the velocities of all the individual molecules must be changing, it is amazing to notice that this distribution remains the same. Now, on this graph, let me point out where exactly are the velocities that we just learned. So in the Maxwell distribution, we will see that the peak of this graph denotes what is known as the most probable speed. The most probable speed means that if you take a snapshot of all the molecules and you see which speed is the most common above all of them, then you will see that it is this speed given by the formula root 2 kBT by m, where kb is the Boltzmann constant, T is the absolute temperature, and m is the molecular mass. You will see that it is this speed that is the most common speed amongst all the molecules at any given point in time. So this is known as the most probable speed. This represents the peak of the Maxwell distribution graph. The second type of speed that we will mark on this graph is the average speed. The average speed is given by root 8 kBT by pi m, and this is C with a subscript AVG. This average speed, as you can see, is slightly lower on the graph as compared to the most probable speed. And the last one is the root mean square speed given by the formula root 3 kBT by m, where again m is the molecular mass. Now these are the three types of speeds, and these formulae are relevant only when you are talking about the Maxwell distribution function. We saw what these formulae actually mean just a while before, and their values will be found for the Maxwell distribution by using these formulae. You can see, as obviously from the graph, that the values which lie to the most right of the graph will be higher than the values on the left, and therefore I can say that the root mean square speed will always be greater than the average speed, which will always be greater than the most probable speed for the Maxwell distribution. Finally, also remember that the Maxwell distribution is plotting the velocities. That means that we are also getting a commentary on the kinetic energy of the molecules, because kinetic energy depends upon velocity. But the kinetic energy of the gas molecules increases with temperature, and therefore if you try to plot the same graph but at a higher temperature, you will see that the distribution spreads out but the relative maximum falls, which means that overall the molecules now have higher speeds. However, the most probable speeds value has gone down, and therefore I will finally say that Maxwell distribution functions spread out with temperatures, but the relative maxima of these functions falls as temperature increases. From the kinetic interpretation of pressure, we can then move on to finding an expression for the kinetic interpretation of temperature. Now, we already said that under the assumptions of kinetic theory of gases, in ideal gases, the molecules are considered to be point particles. We also said that for point particles, there is no internal excitation, which means that there is no vibration and no rotation of these molecules. Finally, because of this, I say that this implies that the point particles have only translational motion and hence possess only translational energy. So the first thing I want to do is write down what is the total translational energy possessed by these molecules. I have already said that the intermolecular forces are negligible and therefore there is no potential energy. However, like we just said, there is kinetic energy and therefore the total energy of a molecule will be nothing but the total kinetic energy. Let's find an expression for the total kinetic energy of a molecule. We do this by using the expression we found for pressure. We already know that pressure is 1 by 3 m by v mc square as we just derived. All I did was take the v to the other side, and this gives me the formula PV is equal to 1 by 3 n mc square. We also know that the ideal gas equation for a particular molecule can be written as PV is equal to n kBT, and therefore I have already the formula first and the formula second at my disposal. From 1 and 2, I can simply equate the right hand sides, cancel off the n's, and I will get equation 3, that is 1 by 3 mc square is equal to kBT. Now I simply multiply equation 3 by 3 by 2 and I get equation 4, which is 1 by 2 mc square is equal to 3 by 2 kBT, and this expression, that is 3 by 2 kBT, is the most important expression when it comes to the total kinetic energy of a molecule. So the total kinetic energy of a molecule is given by 3 by 2 kBT, where kB is the Boltzmann constant and T is the absolute temperature. It is also equal to 3 by 2 PV. Now, before I move on from this expression, I want to make one very important point clear. You must understand the importance of this equation. You are now relating the total kinetic energy of a single molecule to the absolute temperature of the gas. Here you have connected a microscopic quantity, that is the energy of a single molecule, to the temperature, which is a bulk quantity. You have connected these two properties through an equation, and this is why I said that the kinetic theory is a link between the very big and the very small. And you can see that this macroscopic quantity of temperature is connected to the microscopic quantity of energy of a molecule through the Boltzmann constant, and this is the beauty of this equation. So I found the total kinetic energy per unit molecule. I can write this down for a mole, and to do that I simply have to multiply by Na, which is the Avogadro's number. So I get Ke is equal to 3 by 2 Na kBT, but Na kB I know is nothing but the gas constant, and therefore Ke turns out to be 3 by 2 RT, where I replaced Na kB by just the gas constant R. I can also write down the total kinetic energy for n moles, and I do this simply by multiplying the previous expression by n. We saw that Ke for 1 mole was 3 by 2 RT, so Ke for n moles will be 3 by 2 nRT, and nRT can also be written as PV, and therefore I say that Ke is equal to 3 by 2 PV for n moles. Finally, I can also write down the total kinetic energy for per unit mass, and this will be given by 3 by 2 RT by m. So this is the value and expression for the kinetic energy for the molecule, for a mole, and per unit mass. The next important concept that we must discuss is the idea of degrees of freedom. Now, what are degrees of freedom? Degrees of freedom are the independent ways in which a molecule can possess energy, and they are very largely dependent on the way a molecule is allowed to move, and therefore it is associated with the word freedom. The freedom to possess energy or the freedom to move in a certain way will give this molecule a certain amount of energy, and therefore we call them degrees of freedom. So what do the degrees of freedom depend upon? The degrees of freedom of a gas molecule depend upon different things. For example, it depends upon the atomicity, the number of independent particles, which we call A. It depends on the number of independent relations B, and it is given by the formula F is equal to 3A minus B. Let's see what this actually means. Let's say that I have a monoatomic molecule, which means that each molecule of this gas possesses only one single atom, and therefore the number of independent particles is 1, and because the particle is alone, it doesn't have any relations with anybody, and therefore B is 0. From here I can find the degrees of freedom F, which is given by 3A minus B, so 3 into 1, 3, minus 0, which is exactly 3, and therefore I get F is equal to 3. But what happens if I have a diatomic molecule? In case of a diatomic molecule, I will have two independent particles, one relation, that is the B or the bond between these two, one independent relation, and then using the formula 3A minus B, I get F is equal to 5, which means that the degrees of freedom of a diatomic molecule is 5. There are 5 ways in which this molecule can possess energy, and we'll see in a bit how that comes about. Next, I see that if I have a triatomic nonlinear molecule, then in this case the number of independent particles is 3, the number of independent relationship is also 3, and therefore F, which is 3A minus B, comes out to be 6. And finally, if I have a triatomic linear particle, which means that all the 3 lie in a straight line, in such a case the number of independent particles is still 3, but the number of independent relationships is only 2, and therefore the number of degrees of freedom is 7, that is 3A minus B. 3 into 3, 9 minus 2, that is 7. So this is how you find the number of degrees of freedom for any molecule of a gas. The next thing that I want to talk about is the law of equipartition of energy. And this law is closely related to the understanding of degrees of freedom. We saw that there is a formula that is 3A minus B to getting how many degrees of freedom a gas molecule has. And we also commented that degrees of freedom means the number of ways in which a molecule can possess energy. But these are just vague words. Let's see, for example, what I actually mean. Any particular molecule can have different types of independent motions. Now, the first type of motion, which is obvious and we already know, is the translational motion. Now, in translational motion also, a molecule could be moving along the x direction, it could be moving along the y direction, or it could be moving along the z direction. The law of equipartition of Energy simply says that in equilibrium, the total energy is equally distributed in all possible energy modes, with each mode having an average energy equal to half kBt. So that means that the molecule possesses half kBt because it has the freedom to move along the x-axis. It also possesses half kBt because it can move along the y-axis, and half kBt because it can move along the z-axis. But translational motion is not the only motion that a molecule can perform. It may be so for a monoatomic molecule, only translational motion is possible. However, for a diatomic molecule like the one shown in the figure, you could even have rotational motion. In this case, this diatomic molecule can move, that is rotate, in two independent ways, and therefore the rotational modes, which are two in number, will contribute half kBt respectively. Notice how the rotation of the molecule about the line joining the molecules is not considered. This is because this does not change the configuration of the molecule and is not counted as a new configuration. Finally, any molecule can also have a vibrational mode. In vibrational mode, you will see that in a diatomic molecule, the molecules vibrate about their main positions. A vibrational frequency of a molecule actually contributes two modes to the law of equipartition of energy, and actually therefore each vibrational mode contributes 2 times half kBt and therefore contributes a total of kBt amount of energy. But under the assumptions of the kinetic theory of gases, we already said that all the molecules are considered to be point particles, and therefore we will not be considering their rotational or vibrational modes of motion at all. And therefore I will go back to the law of the equipartition of energy, that is, energy per degree of freedom is half kBt, and because I'm only considering translational motion, then at a given temperature the average Ke will come out to be only 3 by 2 kBt, because there are 3 ways in which the particle can move. Now formula, I can also write down the energy of a system if I know its degrees of freedom beforehand. So now how to write down the energy of a system? I saw that for 3 degrees of freedom, the Ke came out to be 3 by 2 kBt, which means if I have f degrees of freedom, the average kinetic energy will come out to be f by 2 kBt. From here now I can write down what is the kinetic energy for n molecules. For n molecules, I simply have to multiply this by n, because what I had found was for one molecule. So for n molecules, it will be f by 2 n kBt. And if I want to find out the kinetic energy for 1 mole, then instead of multiplying by n, I should have multiplied by the Avogadro number, and I'll get f by 2 Na kBt. And n kBt is nothing but RT, because Na kB is nothing but R. And therefore I can also find the kinetic energy for n moles, that is f by 2 n RT. And from here I can also say that for 1 gram the kinetic energy will be equal to f by 2 kBt, which was my original expression, divided by the molecular mass, and this will give me the kinetic energy for 1 gram, that is per unit mass. But kB by m is nothing but the specific gas constant, that is small r. So for 1 gram I can also say that the average kinetic energy is f by 2 RT. Finally, for m grams the average kinetic energy will be f by 2 m RT. So you can see these are different forms of the same exact equation. I just wanted to show you that all of these are derived from the same equipartition of energy law, and you can find them and write them down yourselves if you understand the idea of degrees of freedom. One of the most important applications of the law of equipartition of energy is in finding out the specific heat capacity of a gas. Now, let's revise first some points related to the specific heat capacity before we see how to apply the law of equipartition of energy. Now remember that specific heat of a gas can have a value between 0 and infinity depending upon the conditions in which it is heated, because for different conditions of volume and pressure there will be a different value of the specific heat capacity, and therefore you must specify the condition of volume and pressure under which you are heating the gas before defining the specific heat. And because of this, we have 2 specific heats of a gas. We have the specific heat capacity of a gas at constant volume and the specific heat capacity of a gas at a constant pressure. And these are denoted by the letter small c. So the specific heat, that is C subscript P at constant pressure, and the specific heat, that is C subscript V at constant volume, are given as follows. The first is that the specific heat at constant volume is given by the formula delta Q by m delta T, where m is mass, delta T is the change in temperature, and delta Q is the heat exchanged. Similarly, I can write down the specific heat at constant pressure. The only thing that's different is that the numerator is now the heat exchange at constant pressure. We also know that the relationship between the molar specific heats is Cp minus Cv is equal to R. Keep in mind that here the C's are capital because this equation is for molar specific heat. And the relationship between the molar specific heat and the specific heat is that the molar specific heat is nothing but the molar mass multiplied by the specific heat. So capital Cp is equal to molar mass into small cp, and capital Cv is molar mass into small cv. And therefore the relationship between the molar specific heat and the specific heat is that the specific heat multiplied by the molar mass gives you the molar specific heat. From this now I can see that the gas constant, that is gamma, is given by the ratio either of the specific heats or of the molar specific heats. In both of the cases the ratio will give you gamma. Now let's apply the law of equipartition of energy to finding how we can get the specific heat capacity. First of all, let's write down that for the specific heat capacity of a gas, you can simply apply the law of equipartition of energy and determine the specific heat of a monoatomic, diatomic or a triatomic gas molecule. And how do you do this? You do this simply by using the formula that Cv, where C is the molar specific heat, is equal to 1 by 2 Fr. In this case, the formula relates the molar specific heat at constant volume to the degrees of freedom of a molecule. So from this I can get Cp because we know Cp minus Cv is R. So Cp minus Cv is R, and therefore Cp will just be R plus Cv, and therefore the formula for Cp comes out to be F by 2 plus 1, the whole bracket multiplied by R. So you can see just by knowing what kind of molecule it is, that is, if you know it's a monoatomic molecule, then you know that F is 3. If you know it's a diatomic molecule, then you know that F is 5. And if it's a triatomic molecule, then you have to ask whether it's linear or non-linear. Basically, if you know F, you can straight away find the molar specific heat, and if you know the molar specific heat, you can find the specific heat. Similarly, I can also find the specific gas constant, that is gamma is equal to Cp by Cv. It will be given by 1 plus 2 by F. Now I can also find the specific heat capacity in case of solids using the law of equipartition of energy. Simply speaking, we remember that in solids, the translational and rotational motions are not possible because the molecules are rigidly fixed to their centers, and therefore the only motion that is possible is vibrational motion, and therefore the total kinetic energy in a solid for a molecule is due to vibration only, and therefore each vibrational mode will contribute to the energy of the molecule. But we saw some time ago that each vibrational mode contributes 2 degrees of freedom, and therefore Ke per mode in solids will be twice 1 by 2 kBt, and therefore Ke per mode in solids is kBt, but average energy per atom in 3 dimensions then will be 3 times kBt. So I get kinetic energy per atom in 3 dimensions is 3 times kBt, and therefore total energy for 1 mole of a solid will be 3 kBt multiplied by Avogadro's number, which will give me 3 RT. And then by the definition of the molar specific heat capacity, it will be nothing but delta U, where U is the internal energy, by delta T, and this will give me 3R. And therefore now you will see that the specific heat capacity of a solid is fixed. It is nothing but 3 times the universal gas constant, and we derived this from the law of equipartition of energy. The last concept that I want to talk about is the concept of the mean free path. We already said that molecules in a gas will undergo collisions, and therefore it means that even though the size of the molecules in a gas is finite, they are bound to undergo collisions. And therefore this means that they cannot keep moving in straight lines without being hit by some other molecules, and therefore their paths keep getting deflected because of these collisions. Now the average distance that a molecule travels between 2 successive collisions, this is what is known as the mean free path, and it is denoted by the Greek letter lambda. If you take a careful look at the way a molecule moves within a gas, you will see that it will collide with only those other molecules that lie within a distance d of their centers. And therefore, I can use the fact that d is the diameter of the molecule and n by v is the number of molecules per unit volume to write down the formula for the mean free path. The formula for the mean free path that is given as lambda is equal to 1 upon root 2 pi NVD square, where NV, like I said, is the number of molecules per unit volume and D is the diameter of the molecule. This formula can also be written as 1 upon root 2 kBt by pi d square P, where P is the pressure of the gas. Now this completes all the different concepts that I want to revise with you under the kinetic theory of gases. I hope you understood all the concepts and can quickly revise this. Thank you for watching. So thank you for watching this memory map on kinetic theory of gases. Please subscribe to our channel by clicking on the link here. You can also get your very own target publications book by clicking on the link here. Keep watching for more updates.